Time to combine episode 1 and episode 2. If you didn't tune into the last 2 episodes, check them out. Now, we talked all about matter and all about forces, but what happens when we dig deeper? What do we find about the true reality of nature? What makes up all matter? Particles, waves, something different still? Let's learn how a few key people worked to uncover this mystery. Max Planck. Max Planck was born April 23, 1858 in Kiel, Germany. You'll start to see how physics gets wonderfully less British as time goes on. None of Max Planck's names, and the Germans have quite a few names culturally, particularly older Germans, was actually Max. One of his names was Marx, and at age 10 he signed his name once with Max and continued using it for the remainder of his life. As a young boy in 1867, the family moved to Munich, where Planck met a mathematician named Hermann Müller, who taught him astronomy, mechanics, and mathematics. After Planck graduated at age 17, he chose to study physics at the University of Munich in 1874. Planck performed experiments on only one topic in his entire career. He loved theory and quickly transferred into theoretical physics. By 1877, Planck was attending the Friedrich Wilhelms University in Berlin, where he studied with Helmholtz, Kirchhoff, and Weierstrass. Don't worry if you don't know these names, Planck's about to become bigger than all three put together. It was in Berlin that Planck was studying, mainly on his own, the works of Rudolf Clausius, that he would decide to make thermodynamics his field of study. Thermodynamics was also called the mechanical theory of heat at the time. The field covers the transfer of energy and is perhaps the most accurate field within all of physics, in that the laws of thermodynamics are never broken anywhere in the known universe. In 1905, Einstein published 4 extremely revolutionary papers. One of these papers detailed the photoelectric effect, and proposed the idea of light quanta. Quanta just means a single amount of something. You could call the drips of coffee coming out of a coffee machine quanta of coffee. Now remember, light's a wave, right? Thomas Young proved Newton wrong in 1800 like we talked about in episode 1. Here's where I have to explain that physical laws are always marginally incomplete, and that there are always some extreme cases where when we probe deeper the law breaks down and gives you the wrong result. This is one such case. 99.999% accuracy is what's required to predict the future. This, it was found, is where the 0.001% lies. The joy of physics lies in probing ever deeper into that ever-shrinking decimal place. Now back to Planck. Don't worry, we'll need about 5 or 6 episodes to cover Einstein's contributions in their entirety. Planck absolutely rejected Einstein's theory of quanta of light, in part because it contradicted Maxwell's laws. Planck went as far as to say, quote, "The theory of light would be thrown back not by decades, but by centuries into the age when Christian Huygens dared to fight against the mighty emission theory of Isaac Newton." Huygens may have been okay to cover, but Young did prove the wave nature of light after all, luckily not having to contend with Newton's mighty emission theory. By 1900, Planck became convinced. After working with Boltzmann on statistical mechanics, Planck, as stubborn and conservative as he was, the progress of brilliant physicists created such compelling arguments that Planck got right on board. He published works introducing what is now known as the Planck postulate, that electromagnetic energy could be emitted only in quantized form, like in drips of coffee. These drips would be multiples of elementary units called Planck's constant, or Planck's action quantum. We call it H in physics for short. E equals h nu tells us that the energy of any form of electromagnetic radiation is equal to the amount of drips, or Planck constants, times the frequency of the wave. You can find Planck's constant by taking different forms of radiation with different frequencies and plotting their energy. The slope of the line will be Planck's constant. A small note on why this is called quantum action. Action in physics is defined as energy times time, so the units of Planck's constant are joule seconds. The idea that this quantity acts on the frequency and the result is energy is why the word action is used. By 1910, Planck had become fast friends with Einstein, and they often met to play music together over the years. Planck won the Nobel Prize in 1918 for his work on quantum theory. Small fun facts about Planck. Max Planck's son Erwin was arrested by the Gestapo and executed by the Nazis in 1945 following the July 20th plot to assassinate Adolf Hitler. The death of his son, quote, destroyed much of Planck's will to live. Max Planck died on October 4th, 1947, aged 89. Okay, so now light is a particle again, right? Sort of. Again. Cue the Einstein intro. Albert Einstein. Back to Einstein. Back to the year 1905. Don't worry if your favorite Einsteinian idea isn't in this episode. We'll surely cover it in all of the other ones. We have to touch on what Einstein won the Nobel Prize for, despite the idea being, in my opinion, the least revolutionary of those 4 papers he published in that year, the photoelectric effect. But first, a little about Einstein the man, or Einstein the baby. Einstein was born in Ulm, Germany on March 14, 1879. His parents were secular Ashkenazi Jews and lived in Munich with their son Albert, where his father and uncle founded a company that manufactured electrical equipment. This business failed because they were manufacturing direct current equipment. When alternating current was realized to be the most pragmatic solution to electricity transfer on a large scale, the Einsteins were forced to sell their factory in Munich and move to Milan, Italy, and then to Pavia. Einstein hated school, not so much the material as the structure and methods of learning. He didn't like rote memorization and preferred to work through problems to arrive at solutions, like a real physicist. Einstein was a prodigy of math and physics from an early age. He taught himself algebra, calculus, and Euclidean geometry supposedly when he was only 12 years old. Okay, fast forward to Einstein's contributions. Remember, we said that Thomas Young proved that light is a wave. Well, there was a big problem with this. Think about sound waves. Sound needs a medium to travel through, like air or water, or something to carry it through space. If light is a wave, shouldn't it also need a medium to travel through? Well, physicists thought it did. For a long time, the prevailing theory was that there was a fluid throughout all of the universe called the ether. The ether was the fluid through which light waves travel, just how sound and light waves travel through air on Earth. The only problem was, this ether doesn't exist. Einstein introduced quanta of light, or photons, to fix this problem. Einstein said light is a kind of combination of wave and particle. It can be thought of like a packet, where the packet contains the information of the wave. Einstein combined his theory with Planck's and published his findings of the photoelectric effect, which tells us that shining light of a given frequency on a piece of metal will lead to a proportional voltage and current being produced. But there's a catch. There's a minimum amount of energy needed to bump electrons and get them moving. This is called the work function. Through this thought process, light itself is the medium through which it travels, an extremely elegant theory that would heavily influence the next at least 50 years of physics. Okay, so why do we care? Weren't we talking about atoms in the last video? Why do we care about this wave-particle duality of light? Well, when we hear about quantum mechanics, understanding this wave-particle duality is key to beginning to scratch the surface of the mechanics of quanta. This is because light isn't the only thing that behaves this way. Electrons, neutrinos, quarks, all of these pieces are the building blocks of the universe, and all of them require quantum mechanics to map out their behavior. Einstein was a key player on this journey toward discovering the true nature of the universe. Covering Einstein's life again is absolutely impossible in such a short video, and we'll surely recap his other mind-bending contributions in other videos. He went on to lead the Institute of Advanced Study at Princeton, finally some American universities, and Einstein died April 18, 1955, age 76. Okay, particle wave, sure. But who should we really think of when we think of quantum mechanics? Well, this is a little subjective here, and perhaps I shouldn't jump this far ahead, but we have to cover Erwin Schrodinger to wrap this video up. Schrodinger was born August 12, 1887 in Erdberg, Vienna, Austria-Hungary, to a textile producer father and professor of chemistry mother. He learned English outside of school because his grandmother was British. He studied at the University of Vienna, where he earned his doctorate, and moved to the University of Zurich in 1921. In January 1926, Schrodinger published his Quantization as an Eigenvalue problem. Don't worry if you don't know what an eigenvalue is. This paper described all particles as waves. Through looking at, quote, old quantum theory of Planck and Einstein, Schrodinger created a wave equation that correctly predicted energy levels of atoms like hydrogen. Schrodinger went on to succeed Max Planck at the Friedrich Wilhelm University in Berlin. In 1933, Schrodinger left Germany because he strongly disapproved of the Nazi regime, traveling to Magdalen College at the University of Oxford. That same year, Schrodinger was awarded the Nobel Prize for his wave equation along with Paul Dirac, another incredible titan of physics who we will surely cover in a later video. For this reason, in my most humble opinion, if you're thinking of quantum mechanics, you should think of Erwin Schrodinger and his famous equation. Now, what does Schrodinger's equation tell us? Tells us something that frustrated physicists, including Schrodinger, to no end, and continues to frustrate physicists today. There's a degree of uncertainty at a fundamental level in physics. Let's think about the electron as a wave. If it is a wave, that means it isn't a single point source, like a ball in space. It's a wave with only a certain probability of finding its position in some three-dimensional space. We didn't talk about Werner Heisenberg, but Heisenberg's uncertainty principle tells us that we can only know either the position or the momentum of the electron independently. Once we measure one, we become uncertain about the other by a degree 1/2 h cross, Planck's constant divided by 2 pi. Schrodinger said about this probability interpretation, quote, "I don't like it, and I'm sorry I ever had anything to do with it." He also said, just in order to ridicule the Copenhagen interpretation of quantum mechanics, he contrived the famous thought experiment called Schrodinger's cat, and was said to have angrily complained to his students that, quote, "Now the damned Göttingen physicists use my beautiful wave mechanics for calculating their shitty matrix elements." A wonderful example of a more modern man speaking freely about his field. Erwin Schrodinger died January 4th, 1961 in Vienna of tuberculosis. He was 73 years old. This concludes episode 3. Stay tuned for episode 4 where we'll hear more stories about great people in physics.